It's funny, isn't it? We often think about math as this like really abstract thing, stuck in textbooks and classrooms. But then you see how things in the real world just naturally fall into these like ordered patterns.
Right.
The way a city's population might change every year, or even something simple like how your bank balance grows with interest.
Yeah.
You suddenly realize, oh, sequences are everywhere. It even makes me think about that Dedekind quote. Natural numbers are the product of the human spirit.
Yeah.
Quite a grand way to think about these ordered steps,
It
right?
is. Yeah. It sort of underlines how these fundamental parts of math
Mhm.
are like a reflection of something we just inherently understand about how the world works.
Hmm.
So this deep dive is all about exploring that world, the world of sequences and series.
Right.
Based on all this great material you shared, you can think of it like we're sifting through everything, pulling out the really important stuff to understand why these concepts are so important.
Exactly. So we'll be looking at the main types of sequences and series. Arithmetic progressions, the ones where you keep adding the same amount each time.
Right.
Then there are geometric progressions where you multiply by the same factor over and over again.
Yeah.
And then there are those really fascinating sums of special series, like figuring out the total of the first in natural numbers or their squares or even their cubes. We'll also touch upon that elegant Fibonacci sequence and the concepts of arithmetic and geometric means.
Right. And as we go through this together, don't worry if you don't feel like a math whiz or anything. We'll keep it accessible, keep it interesting, really highlight the key takeaways, those aha moments that help you connect all the dots.
Okay, so let's start with the very basics. What exactly is a sequence? Our sources define it as an ordered collection. So it's not just a bunch of random things thrown together. The order matters. The order they appear in is really fundamental to the whole concept. It's like, think of a line of people waiting for something. There's a first person, the second person, the third, and so on.
Perfect analogy.
That's it. And the material gives some really good real-world examples when we talk about how a population changes over time,
Right.
or how the money in your bank account grows because of interest, or even, how a car or anything really loses value every year through depreciation. These are all ordered sequences. Each event, each change happens in a specific order.
Absolutely. Each one after the other.
And each individual thing in that sequence, each person in our line, is called a term.
Okay.
And we have a way of labeling those terms, which is super helpful. $1 for the first term, $0 for the second, and so on until you get to up $1,
Right.
which represents the nth term.
Hmm.
You can think of a non-oral way to refer to any term in the sequence just by specifying its position. It's kind of like it's like assigning each spot in line a specific number.
It's a good way to think about it. Yeah.
Now we need to differentiate between sequences that continue forever
Yeah.
versus those that actually have a defined ending point.
Right.
So like the example about tracing your ancestors back 10 generations,
Okay.
that's a finite sequence, right? It stops at a certain point.
Yeah.
But if you think about dividing 10 by 3,
Yeah.
you get 3, 3.3, 3.3, 3 repeating.
Right.
That decimal goes on forever.
Right.
That's an infinite sequence. Now, here's where things get a little more interesting. How do we figure out what comes next in a sequence? The sources highlight a few clever ways to do that.
Okay.
First, we can use algebraic formulas. So for example, the formula 1 equals 2n21 will give you the sequence of even numbers, 2, 4, 6, and so on.
Okay.
You plug in the position n, and boom, the formula tells you the term at that position.
That makes sense.
Similarly, the formula 1 core in 2n1 gives you all the odd numbers. Another way to define a sequence, and this is really powerful, is through what's called a recurrence relation. The Fibonacci sequence is probably the most famous example of this. It starts with 1, and then every term after that is the sum of the two terms before it. So $1, $2 along one $1, and then 1A2 plus AN1 for any greater than 2. It's like the sequence is built on its own past,
I like that. Yeah, it's building upon itself. Yeah.
Then you have sequences defined by a specific rule, like the sequence of prime numbers, 2, 3, 5, 7. There's no simple, algebraic formula to directly calculate the nth prime number. You just have to know what a prime number is and generate them in order.
Right.
And that shows us that not every sequence has, a neat, clean equation that describes it.
True. And the material also introduces a bit of a different way to think about sequences, and that is as a function.
Okay.
You can almost imagine a machine, right, where you feed in a natural number, 1, 2, 3, representing the position in the sequence, and the machine spits out the term that belongs in that spot.
I like that.
And sometimes you'll even see the notation $am instead of A, which really emphasizes this idea that a sequence is kind of like a function, right, acting on these natural numbers.
Right.
It's a useful perspective, but abstract, but useful.
Okay, so we've covered sequences. They're ordered collections.
Yes.
Now, what's a series? It seems like the natural next step.
It is. A series is simply the sum of the terms in a sequence.
Okay.
So if you have your sequence, A dollar, A2, A33, and so on, the series that goes with it is just A dollar plus A2 plus A33, and so on. Just like sequences, a series can be finite or infinite, depending on whether the original sequence was limited or, just went on forever.
Okay. Now, writing out all those plus signs, that can get pretty tedious, right? Is there a more compact way to represent a series?
There is. There is. And it's called sigma notation. It uses this Greek letter, sigma, which looks like this, some dollars.
Yeah.
So if we have a series, A dollars plus A2 plus Dana, you can write that much more concisely using sigma notation. The K there is just a counter. It starts at 1, goes up to N, and it tells you which terms to add together.
Okay.
Think of it as like a mathematical shorthand for doing addition over and over again, following a specific rule.
Now, the material makes a very subtle distinction here, and it's important. When we say series, we mean that expression where you're adding the terms together.
Right.
But the sum of a series is the actual number you get after you do the addition. So, for example, 1 plus 3 plus 5 plus 7, that's a finite series. And when you actually add those numbers up, the sum of the series is 16.
That's it. That's the difference. The series is the instruction to add. The sum is the result you get after actually adding it up. And the text gives a few examples that kind of illustrate these ideas. Example 1 shows you how to find the first 3 terms of a sequence if you're given the formula for the nth term.
Right.
Like 1 belongs to 2 metals plus 5, 5, or 1 recus 3 and 1 4 is 3. You just plug in n equals 1, 2, and 3 into the formula.
Okay.
And example 2 is pretty straightforward. It just asks you to find the 20th term of a sequence where 1 equals n1, 2, and 3 plus n. Again, you're just substituting n equals 20 to get that specific term in the sequence.
Right.
But example 3 is pretty useful because it actually links those ideas of sequences in series. It gives you a sequence defined by a recurrence relation. A dollar equals none, and then 1 plus 2, 2 for all n greater than or equal to 2. We see how the first few terms are generated, 1, 3, 5, 7, 9. And the corresponding series is just those terms with plus signs in between, 1 plus 3 plus 5 plus 7 plus 9, and so on.
Got it. Okay, so we have a good grasp of the basics. Let's move on to specific kinds of sequences. Let's start with the arithmetic progression, or as we often call it, the AP. I remember these from school. It's all about adding the same number repeatedly.
Exactly. Exactly. An arithmetic progression is a sequence where the difference between any 2 terms that are right next to each other, it's constant.
Right.
We call that constant difference.
The
The relationship between one term and the next is just A plus 1 equals A plus D dollars. It's like, climbing a set of stairs.
Right.
Where each step is the exact same height.
Okay, yeah.
And the standard way to write out an AP is to start with that first term,
Right.
which we call A,
Uh-huh.
and then you just keep adding D to get each next term.
Right.
So it looks like A plus D plus 2D, and so on. This leads us to a super useful formula for finding any term in the sequence, the nth term, and that's 1th and 1DO. This saves you so much time and effort, because you don't have to list out all the terms one by one if you only need one that's, further down the line.
Yeah.
The material points out some basic properties of APs that are worth noting.
Okay.
If you take an AP and you add, subtract, multiply, or even divide every term by the same constant, the resulting sequence will still be an arithmetic progression.
Right.
Of course, assuming you're not trying to divide by 0.
Right.
The starting term and that common difference, they might change.
Yeah.
But the fundamental structure in the AP stays the same.
Right.
So we have these kind of standard shorthands we use. A for the first term, L for the last term if the AP is finite, D for the common difference, N for the number of terms, and then sans enough for the sum of the first N terms.
Okay.
And speaking of the sum, we have a couple of handy formulas for sans that are good to know.
Okay.
Sans enough 2A plus N1D,
Yeah.
and sans enough plus L done. The second one is especially useful if you already know the first and the last term. So those sum formulas are really important, and the examples really show how they're used.
Okay.
Example 4 gives you a classic problem. If you know the nth term of an AP is N, and the nth term is M, where M and N aren't the same,
Right.
how do you find the picton term?
Okay.
So the way you solve this is by setting up 2 equations using that formula for Nr, one for the nth term, one for the nth term, And then you solve those equations simultaneously to find A and D.
Okay.
Once you have those, you can plug them back into the AND formula to find the pith term, which interestingly turns out to be 1 class MP. It's a nice illustration of how algebra can help us understand these relationships within sequences.
Right.
Example 5 is interesting because it gives you a formula for the sum of the first n terms, sum and p plus fram 1 dol and 1 to q, and it asks you to find the common difference like key. The key here is remembering that connection between the sum of a series and the individual terms. Right. That nth term is just the difference between the sum of the first n terms, which is 7n, and the sum of the first n minus 1 terms, 7n.
Okay.
By finding those first two terms in this way, we can easily calculate the common difference, which in this case turns out to be q.
Okay.
And then example 6 deals with comparing two different APs. You're given the ratio of the sums of their first n terms as 3 merrills plus 8, 7 plus 15 dentures, and you need to find the ratio of their 12th terms.
Okay.
The trick here is to realize that the ratio of the kth terms, you can find that by substituting $1 to K11 into the ratio of those sum formulas.
Okay.
It's kind of a neat shortcut that avoids having to figure out the individual first terms and the common differences of each AP. For the 12th term, we'd set K equals 12, 2. So it would be 2 times 12 minus 1, which is 23. Plugging that into the given ratio gives us 7 to 16.
I see.
Nice little technique.
Yeah, it is. Okay.
And finally, example 7 gives us a practical scenario. You're calculating someone's total income over 20 years if they start with a certain salary and get a fixed raise every year. This is a direct application of the sum of an AP, where the initial salary is A, the annual raise is D, and the number of years is N. Plugging those numbers into the formula, we find that total income is $79,000. It's always satisfying when you see these kind of abstract math ideas applied to concrete problems like that.
Yeah, absolutely. So building on that concept of AP, we have the idea of the arithmetic mean,
Right.
the AM. So for any two numbers, let's call them A and B, their arithmetic mean, usually represented as A, is basically just the average, 1AA plus B2I. And those three numbers, A, A, B, they form an arithmetic progression. The AM is the number you can put in between two others to keep that constant difference going.
Exactly, exactly.
Yeah.
But what if we want to put more than just one arithmetic mean between two numbers? Let's say we want to insert an arithmetic means $8, A22, all the way up to A to 2 between A and B.
Right.
So that the entire sequence, AA1, A2, 8, and B, forms an AP. Well, in that scenario, B becomes the den plus 2th term in this new AP. Yeah. We can use that formula for the nth term, a den 1 plus n1 to d to figure out that common difference den. Here, B is A plus 2.
Okay.
So Brie goes A plus n plus 2, 1 to Diller, which is just A plus n plus 1 to Diller. Solving for den gives us frac B AM plus 1.
Right.
And once we have den, that common difference, we can find each one of those n arithmetic means that we inserted.
Okay.
First one, A del B, is simply a plus den. The second one, A till 2, is a plus 2 den, and so on, up to the nth one, on all is plus into Galler. There's even a general formula for the K inserted AM, AK always OK plus ski to Galler, which is equal to A plus frac B AM plus 1.
Okay.
Example 8 gives us a clear picture of this. It asks us to insert 6 numbers between 3 and 24 so that it forms an AP. So here of Lanellers O'Day, Balox's 244, and we're inserting one in Balozzi's 666 means. The total number of terms in this AP is going to be 6 plus 2, so 8. We can calculate the common difference, D. D equals frac 24, 3, 6 plus 1 equals 3, 3, and then we just find each of the 6 numbers by adding D repeatedly to the first term. 3 plus 3 equals 6, 6 plus 3 equals 9, and so on, which gives us the sequence 6, 9, 12, 15, 18, and 21.
Got it. Okay. Now let's shift gears a bit and talk about another important type of sequence, the geometric progression, which we often shorten to GP.
Right.
Instead of adding, we're going to be multiplying by a constant ratio here.
That's right. In a GP, every term after that first one is found by multiplying the previous term by a fixed value, which is what we call the common ratio, RR.
Okay.
So the relationship between consecutive terms is just frac plus 1 IR doc. The standard form of a GP looks like this: R2, R3, R2R, and so on. That is still our first term. You can think of it like something that grows or shrinks by the same percentage in each step.
Okay.
The material gives a few examples of common ratios.
Okay.
So for the sequence 2, 4, 8, 16, and so on, the common ratio is 2. For the sequence $1, frac 1, 3, frac 1 on, so on, the common ratio is a frac 1, 3. And for $0, 001, 0.000000, so on, the common ratio is 0.00011. And just like with APS, we have some standard notations that we use. A is still the first term. R is now the common ratio. L is the last term, if it's a finite GP. N is the number of terms, and C over R is the sum of the first n terms.
Got it. So what's the formula for the nth term of a GP?
That formula is 1 and nigh on 1. And just like the formula for the nth term in an AP, it's super useful because it lets you calculate any term directly, just knowing the position, the first term, and the common ratio. And just like sequences in general, geometric progressions can be finite or infinite,
Right.
meaning they have a fixed number of terms or they go on forever. And that leads us to finite and infinite geometric series when you add up all those terms.
Right. Now, how about the formula for the sum of the first n terms of a GP?
So for that, it actually depends on the value of our common ratio, R. If $3.01, then every term in the sequence is just 8 repeated on times. And the sum is simply sin her n equals naught.
Okay.
But if Rn is not equal to 1, then we've got two equivalent formulas. Sin her n, frac around 1. You can use whichever one's more convenient. Often it depends if the absolute value of R is less than 1 or greater than 1 to avoid having to deal with those negative numbers in the denominator.
Makes sense. Now, the material has several examples for GPS. Let's take a look at those.
Sounds good.
Okay, so example 9 says, find the 10th term and the general nth term of the GP, 5, 25, 125. So here, the first term A is 5. The common ratio R is also 5. Using the formula 1, the 10th term is $5, 100, 5 tenths 1, which is 510, and the general nth term is 1, 5 10 5 1, which simplifies to $5.
Yep. A straightforward application of that formula.
Right. Example 10 poses the opposite question.
Right.
Which term in the GP 2, 8, 32, and so on is equal to 131,072?
Okay.
So in this GP, the first term A is 2, the common ratio R is 4. We need to find that value of n such that R and N won 1310722, which gives us the equation $2. It's got up 4n1. 4n1 equals 131a is 722. And solving for n, we find that 131,072 is actually the 9th term of the sequence.
That's right.
Okay. Example 11 gives us two terms of a GP.
Okay.
The third term is 24, and the sixth term is 192.
Good.
We need to find the 10th term.
Yeah.
So we can use the on-and-one formula to set up two equations. We get R2 equals 244, and R5 equals 122.
Okay.
If we divide the second equation by the first, the A cancels out nicely, and we get 3d3 equals $88, which means our common ratio, R, is 2.
Okay.
Now, we plug that value of R back into either of the original equations to solve for A, and A turns out to be 6. And finally, we can calculate a $10, which is R99, which is 6 times 2 to the power of 9, giving us 3,072 for that 10th term.
That's right. It's a good illustration of how you can kind of work backward.
Right.
From some given terms, you can find other terms in the GP.
Exactly. Now, example 12 is about finding the sum of the first n terms and the sum of the first 5 terms of this geometric series, $1 plus frac 3 plus fracto. So here, the first term, A, is 1, and the common ratio, R, is frac. We plug these directly into the formula for the sum of the first n terms, which gives us frac 1, and that simplifies to 3 1 terms. To find the sum of the first 5 terms, we just put 1 aisle 5 5 into that formula.
Makes sense.
Example 13 wants us to figure out how many terms of the GP frac 3 3 are needed to reach a sum of frac 12.
Good.
In this GP, 1 of 3 4 or 4 3, 12, and 12. We set the formula for 7 aisle equal to frac 12, and we solve for n. After a bit of algebraic gymnastics, we find that 1 used $10. Example 14 presents a situation where we know the sum of the first 3 terms of a GP is frac 12, and their product is -1. We need to find the common ratio, R, and all 3 terms. Now, when you're dealing with the product of terms in a GP, it's often helpful to think about the first 3 terms like this, fract R, because then their product is simply fract R, which is just A33.
Right.
And since we're told the product is -1, we know $2 implies R fract R, meaning A has to be -1.
Okay.
Now, we can use that fact about the sum of those first 3 terms, fract R plus R roll, and plug in 1 mated of $1 to get an equation just in terms of R. Solving that equation, which is probably going to end up being a quadratic in R, will give us the possible values for the common ratio, and then we can find the corresponding terms of the GP.
Okay.
Example 15 introduces this interesting series, 777, 777, 7,777, and so on.
Okay.
And it wants to know what the sum is up to in terms. Now, this isn't your typical geometric progression, right? But we can use this clever little algebraic trick to relate it to 1. We can factor out a 7.
Okay.
And then we multiply and divide the remaining series by 9.
Right.
That lets us rewrite each term like 999, as a power of 10 minus 1. 10 minus 1, 100 minus 1, 1000 minus 1.
Okay.
Now we have a sum of geometric series, which we can evaluate using the standard formula.
That makes sense.
Example 16 gives us another real-world use for geometric progressions.
Okay.
So if you think about your family tree,
Yep.
you have 2 parents, 4 grandparents, 8 great-grandparents, and so on.
Right.
The number of ancestors in each generation going back forms a GP with the first term, A, equal to 2.
Right.
And the common ratio, R, also equal to 2.
Yep.
So if you wanted to find the total number of ancestors you have over, let's say, 10 generations, you'd calculate the sum of the first 10 terms of this GP using the formula for Sisson et al. Now, just as we had arithmetic means, we also have geometric means. If you have 2 positive numbers, A and B, their geometric mean, which we often call G, is squared or da.
Okay.
And the 3 numbers after G, B, B form a geometric progression. The GM is the number you can insert between 2 positive numbers so that they have that constant multiplicative ratio.
Exactly. And if you want to insert any geometric means between those 2 positive numbers, A and B, let's say G dollars, G2, F on GN, all, so that the whole sequence, AG1R, G2R, and DNB is a GP, you can calculate that common ratio R. Since B is now the ARN plus tough term in this GP, we know by ARN plus $1.
Right.
Solving for R gives us frac ON plus 1.
Okay.
And once we have the value of R, we can find each of those n geometric means that we put in. The first one, G dollars, is just ARN jot. The second G dollars is ARN 2, and so on up to $900, which is ARN dollars. Generally speaking, the KG in geometric mean you insert is going to be GKON or UF on N plus 1. Example 17 shows this in action. We have to insert 3 numbers between 1 and 256, so the whole thing's a GP.
Okay.
Here, one other bottles is equals $506, and we're inserting $1 equals 33 means.
Okay.
So the common ratio R is going to be frac 13 plus 1, which is 256 frac 4, giving us plus or minus 4.
Right.
This gives us 2 possible sets of geometric means. If R is positive 4, the means are 4, 16, 64. If R is negative 4, then you're